Hello and welcome to Nets, Plans and Elevations Shape with me, Bill Henning. Now the objective of this session is to draw 2D shapes and demonstrate an understanding of line symmetry and knowledge of the relative size of angles, interpret nets and simple 3D shapes, interpret plans and elevations of simple 3D shapes, understand and use common 2D representations of 3D objects, and draw 3D shapes to include plans and elevations. Now let's look at 2D shapes, because 2D shapes are flat objects and they have lines of what they call symmetry. This word will come up quite often in your exams. Okay, now a line of symmetry splits a shape in half where both halves are a mirror image of each other. So if you imagine a butterfly wings that fold up, you can see they're very symmetrical, there won't be any overlapping. Alright, to test whether a shape has a line of symmetry, you could fold the shape along a line, and if it was a line of symmetry, both sides would fold exactly over each other. Some shapes like rectangles and squares have more than one line of symmetry. So let's develop that. Okay, so let's look at a square first. You can see the square there. Okay, it has 4 edges, 4 vertices. You might hear that word vertex. It just means corner. Okay, and 4 lines of symmetry. And you can see if you fold it that way, it's a mirror image. If you fold it that way, again, a mirror image. And again, 4 ways. So you can see there are 4 lines of symmetry. Now let's look at a rectangle, a similar type shape. Okay, again, it has 4 edges. And again, it has 4 corners or vertices. Okay, but watch this time. It only has 2 lines of symmetry, because you can only fold it in half that way and fold it in half that way, and that's the difference between a square and a rectangle. It only has 2 lines of symmetry, not 4. Now let's look at triangles. Okay, you can see this triangle here. Okay, it's an isosceles triangle. It has 3 edges. Okay, 3 vertices or 3 corners, and you can see it only has 1 line of symmetry right down the middle. You can't put that line any other way to fold in half. And you can see that it's a mirror image. And that there is known as a line of symmetry. Again, this will crop up from time to time in your exams, so it's worth remembering. Okay, now let's look at an equilateral triangle. This means that all the sides are the same size. Okay, and if you remember the angles session, all the angles are the same size. Okay, and you must add up to 180, so all the angles will be 60 degrees. Now again, you can see there are 3 edges, just like the isosceles triangle. There's 3 corners, again, just like the isosceles, but this time there is 3 lines of symmetry, because you can see if you fold it that way, you have a mirror image. If you fold it that way, you have a mirror image. And if you fold it that way, it has a mirror image. Okay, so it has 3 lines of symmetry. Now you try it. How many lines of symmetry does the shape below have? Pause the video and have a go. So how did you do? There's 1, there's 2, there's 3, and there's 4. So this shape has 4 lines of symmetry, and if you got 4, well done. Let's look at circles. Okay, now a circle, you have your circumference, okay, or the edge or the perimeter. All right, so you have one edge, circumference, also known as perimeter. You have a diameter. Now the diameter runs from edge to edge through the middle of the circle. All right, and then you have the radius. Now you'll notice the radius is half the diameter. Again, when it comes to things like area and volume, that's very important to know, that the radius is half the diameter. It has no corners, okay, but it does have infinite lines of symmetry. It doesn't matter which way you fold it, it will always be, if it's a pure circle, then it will never overlap. So it has infinite lines of symmetry. And the distance around the circle is 360. And if you remember your angles session, then 360 is a magic number when it comes to angles. Okay, so now you have a go. I want you to tick the shapes below that have more than 2 lines of symmetry. So let's go through them. Do you think that has more than 2? Doesn't. What about this shape? Do you think that has more than 2 lines of symmetry? Definitely. It's infinite, isn't it? What about this shape? Do you think that has more than 2? Definitely. Okay, you can see there's 1, 2, 3, 4, 5. What about this shape here? Does that have more than 2 lines of symmetry? Nope. Let's try the last shape here. Does this have more than 2 lines of symmetry? How did you do? Yeah, definitely. So if you got these in your answers, well done. Now let's look at dimensions. Okay, 2D shapes are two-dimensional. They have a length and a width. Very important when it comes to working in area. Okay, so you can see there's a shape there. Okay, it's got length and it's got width. Could be a square. Okay, and 3D shapes have 3 dimensions: length, width, and height. And again, that's important when you're working in volume. So you can see with the square or rectangle here, you have length and width. And now you're adding depth, or it's length, width, and then height. Okay, and that is 3-dimensional. Okay, again, it's very important to remember that when you're working in area for 2-dimension, a flat surface, and 3-dimensional when you're working in volume, the space you're occupying within a shape. Okay, now let's look at 3D shape characteristics. It's worth knowing these things, especially when you're working in area and volume. It's always worth knowing what shapes have what characteristics belong to what shape. So let's take this cube or cuboid. You can see there it has edges. Okay, you can count how many edges there are. There should be, I think it's 12 edges. It has a base, which is a part underneath you can't see. Okay, you have vertices. So in this case, it'll have 8 corners. Okay, and you have faces, and you can see this 6-sided shape has 6 faces. So these are the characteristics of this particular shape. Right, you will need to recognize certain 3D shapes when you're doing your maths. Okay, so it's worth learning the names of the following 3D shapes. Okay, some you may know, some you may not. Okay, so let's look at the first one. That's a cuboid. Okay, because all the sides are the same size. Okay, you have a rectangular prism. Okay, cylinder. You may know that one already. This one is a sphere or a ball shape, same thing. Okay, this one here is a squared base triangular prism. You can get triangular prisms just triangular. And this one here is a cone. All right, so these are the main shapes that tend to pop up in your exam papers. Okay, you just need to remember what they're called. Here's an example of working with dimensions. Leonardo is designing a box to hold 5 DVD cases. Now each DVD case is 14 centimeters long, 1.4 centimeters wide, and 19 centimeters high. Okay, and you can see he has to fit them in this case here. So the height and the width fit. So if you look at there, the height is 19 centimeters, so that fits snugly in that dimension. The case is 14 centimeters long, so it'll fit lengthwise in the casing. That just leaves us with the width here. Okay, and you can see that every one of the DVDs is 1.4 in width. So all you do is take this 7 centimeters and divide it by 1.4, and that will tell you how many DVDs you can fit in there. So you need to find out how many DVD cases will fit along that length. Okay, and this can be done just by simply dividing the 7 by 1.4. Okay, and if you do that, 7 divided by 1.4 equals 5. So that means that you can fit 5 DVD cases into that casing. Okay, so now you try it. Anne wants to put as many books as she can in a shelf on the wall. How many books can fit in the shelf? So there's your shelving. All right, she wants to fit as many books across here as possible. Okay, there's the dimensions of the books. Okay, so how many of these books can she fit along there? Pause the video, have a go. How did you do? Right, let's have a look. Okay, so you can see the height and width are fine. It's just how many you can fit across there, and the width of the books. And you can see the width of the books is 6 centimeters. So you take 92, divide it by 6, and that gives you 15.33. Now you can see that you can't get 0.33 of a book. So 15 books can fit along that shelf quite snugly in there like that. So if you've got 15, great answer, well done. Now, a front elevation, this is one area where learners tend to drop points because they don't understand what the word elevation means. Elevation just means the angle that you're looking at an object from. Okay, so a front elevation is a view from the front, and the side elevation is a view from the side of an object. And the plan is just a bird's eye view from above. So if you imagine you're looking at a map, you're looking at a plan. Okay, a bird's eye view from above. Okay, so let's have a look. Now, draw a plan, a front elevation and a side elevation of the following 3D object. Now you can see here, the elevation is the angle you look at something from. Okay, so if we want to draw a front elevation, all we would see, imagine you were standing here, all you would see is this box here, and that box there. So that was all you'd see. You wouldn't see these side parts, you wouldn't see the roof, all you would see is the front faces, these three faces. All right, and if it's a side elevation, you're standing here, you can see all you would see is these two faces. You would not see the top part and you wouldn't see the sides. So that's your side view or side elevation. And finally, the plan. Imagine you're looking at from above, from a bird's eye point of view. Okay, you can see there as you do that, then you can see that's what it would look like from a bird's eye point of view. Here are some further examples of what has just been said. You can see there you have this shape here and you've got a side and front elevation. Well, there's, if you look at it from different angles, you can see there, if you're looking from above the plan, all you would see is these darkened squares. If you're looking at it from either side, you can see you would only see three of the faces depending where you're standing. So the elevation just means the angle you're looking at an object from. Here's another one, funny U-shaped type thing, plan and side elevation. There's your plan, that's your plan. You're looking down at it from a bird's eye view. Okay, and there's your side elevation. All you would see is that face there. You wouldn't see this side, you wouldn't see the top. Okay, and the final one here is this funny looking shape. All right, and if you look at it from the top, all you would see is the three top facing, the top parts. If you look at it from the front, that's a front view, all you would see is the three front faces, that one there, that one, and that one. Okay, you wouldn't see this, you wouldn't see the top or the sides. And then the side elevation, looking at it from the side. And that's what plans and elevations are. Okay, so now you try it. Which is a plan view of the object shown? So pause the video, have a think about it. Which one of these objects here is a match for the plan view of that shape there? Okay, how did you do? If your answer was D, then well done. Right, which left side elevation of the object is shown? Okay, so pause the video. Which one do you think would match that? Now this is a question a lot of people get wrong, okay, because they don't understand. You have to imagine when you're standing at position what it would look like, okay, and this can deceive some people. So how did you do? Right, now the answer is C. Okay, most people pick this for some reason because they think that I don't know, I can't understand why, but you wouldn't see this side here, would you? All you would see is the end gable and the roof slanting away from you. So if you look at that part there, only on the other side, that would be the opposite of that there. All you would see is that and the side gable. Okay, to see that angle, you'd need to be standing here in this view here, but you're not. You're standing on this view here, looking at it from that angle, side elevation. Right, a net. Let's look at a net. A net is a 3D shape that has been unfolded. All right, you need to be able to recognize and draw nets. Now, a net shows each face of the shape laid out and flat. A 3D shape often has several different nets. Below are some examples of nets of a cube, and there's many more. All right. So you think about this cube here, okay, and you can see there's a cube, okay, and these are the different versions of it. But if you imagine, and this is where you have to use your imagination, because you have to understand, once you deconstruct that cube into a flat pack, basically, you have to remember that it has four sides. These are the four sides. It has a lid and a base. And if you look at this one here, there's your four sides, there's your lid, and there's your base. There's your four sides, there's your lid, and there's your base. And again, there's your four sides here, okay, and there's your lid, and there's your base. So don't get caught out with these shapes. Now each net that we've seen before can be folded up to construct a cube, just like this. So there's your net. You're starting off with your net, okay, and you want to construct that into a cube. So again, you can see there one of your sides is folded up. There's your next side folded up, and if you follow that pattern, you bring your sides up, and you can see there that you close it with the lid. So you're just constructing, or depending on the question, deconstructing an object. So the object, the net is the flattened version of the three-dimensional object. Okay, so here's some further examples of nets of cuboids and nets of prisms. Okay, you can see there, if you take these dimensions, okay, if you take these dimensions here, and if you flatten them out, you can see that they match exactly the dimensions of the two-dimensional shape. Now, this is what you do when you're working out the surface area of a cube, for example, cuboid, okay, or a triangular prism, rectangular prism. You just flatten out and then you work out the area of each separately and add them together to work out the area. Okay, and here's the nets of a prism, a triangular prism. When you open that up flat, you can see it has three sides and two ends. Again, and if you had to work out the area of that, you would follow the rules that you were taught in your area and volume session. Another couple of common shapes you may come across. Now here's the pyramid, okay, and you can see if you open that pyramid up, you've got the square base, okay, and you've got three triangles, all the same dimension, okay. So again, from that you can split it down and work out the area. And here's your cylinder, okay. When you split that open, you can see there that there is what it looks like net form, and from that you can work out the area of that cylinder. All right, so that's two-dimensional representations of three-dimensional shapes. Okay, so now you try it. Which of the following nets can be used to form a cube? Take your time, pause the video and see if you can get the correct answer. Just remember, you have four sides, a lid and a base. So how did you do? All right, well, A is certainly will be able to form a cube, and C. So if you've got A and C, well done. If you look at the other two, they've got two lids on one side. Where's the base? That sort of thing. You've got two lids on that side and a base, so you've got too many in that case. Now, which one of these nets will fold into this shape? All right, so have a look at the four shapes in front of you. Okay, which one? Pause the video, have a go and see what you think. Okay, if you choose the last one there, then you did fantastically well. And that is nets, plans and elevation and shape. So thank you very much.